Okay, we'll begin then, and happy Monday to you guys. I hope you guys are all doing well. I have posted your first homework assignment that is available under week 2, and you know, as per tradition, it's fairly long. So please get started on it soon, and it'll be due next week, next Monday. So you got about a week to do it. You know, as you get stuck or if you've got questions, post them on Campus Wire, and we'll work through it. So, okay, today we will look at cross-validation. All right, so cross-validation is a strategy for us to kind of help us choose a model. All right, so we are comparing different models, and we are going to, when we do that, we get a cross-validation score, and I'll explain how we arrive at a cross-validation score. And using the cross-validation score, we are going to be able to compare a few different models. All right, and so what we're going to do is we're going to look at the Olympic data, and this is kind of the eventual goal of what we want to do. And so on Friday we did this. We created the Olympic data, and we said, you know, over time, as time has gone on, the winning race time for the 100-meter dash has gotten faster and faster and faster. Okay. And so, you know, we tried fitting a few different models. We did a linear model, and then we did a quadratic, cubic, 4th order polynomial, 5th order, 6th order. We tried several different polynomials of different degrees. And if you plot them all, okay, so these are just kind of commands to plot the predicted values versus the year. This is what the lines look like, and we can see on top of that are the actual observed values, and we want to know how well do these things work. Okay. So the if you take 101A, you know, the classical approach for model selection requires us to kind of think about the variables. You know, we have to ask questions like, does it make sense for race times, okay, to have a quadratic or cubic relationship to time, or the year where when the race was held? Okay. Does it make sense for there to be a 6th order relationship? Okay. And these kinds of questions are really hard to think about, right? So like, what does it mean to have a cubic relationship to the year in which the race was held? I have a hard time answering such a question, okay? And it's difficult to even think about that, all right? You have a couple tools in there, like AIC and BIC, to help in the model selection procedure, and those are generally balances. It's a balance between the you know, sum of squares with kind of against model complexity. As you increase your model complexity, the AIC or BIC measures will change as well. And so so you have things like that, right? So every time you use an additional, each time you make your polynomial model, you know, a higher order, you have an additional parameter to estimate, and every time you have to estimate another parameter, you're using up an additional degree of freedom. And in general, what we want is we want our models to have kind of the best predictive performance balanced with the model complexity. Okay, and so anyway, the classical approach is good if you have domain knowledge, if you can understand and think about and reason about the relationships between variables, but sometimes it can be a little arbitrary, the decision making. You go, I'm going to decide this versus this, and that kind of thinking can feel a little arbitrary. And so cross-validation removes a lot of that thinking and just uses a validation approach. It just says, how well can this model make predictions on new data? So you're going to present it with basically new data, And you're going to say, well, how well does it predict this new data? And so in order for you to have new data, okay, we have to kind of pretend something is new data. So you only have a certain set of observed data. And so what you're going to do is you're going to split it into two parts. You're going to split it into a training set and a validation set. The validation set is going to be your quote new data, right? And so what you do is after you split it into a training set and a validation set, you use the training set to fit the model. In that case, it means just kind of finding the slope and the intercept if you're doing linear regression, or if you're doing any kind of higher order model prediction, it just basically means finding that vector of coefficients, that vector W hat. Okay, so that's going to be training. And then once you've fit the model using the training set, you have those estimated coefficients, those estimated parameters, you're going to use those values to make predictions on the validation set, right? So you're going to use some kind of predict function, or you're going to do X times W hat as a matrix operation, or whatever you want it to be. And then you're going to use some kind of metric, okay, to measure how well the model performs at making predictions. So, okay, so once you have your predicted values, you are going to compare the predicted values to the actual values, right? So you're going to measure how well did the your model perform in terms of predicting the new values that it hasn't seen. Okay, so you make predictions on the validation set, and you compare the actual validation answers to the predicted values. Okay. And you do this for the different kind of models that you want to compare, and then you compare the metrics across those models, and you choose the best performing model there. All right. So I'm going to start off by explaining leave one out cross-validation. Okay. In leave one out cross-validation, the training data is going to be all of the available data that you have, except one observation. Okay, you're going to leave one of those observations out, and everything else is going to be the training data. And each observation in your observed data is going to have a turn at being in the validation set. Okay, or being the validation set. So if you have a total of n observations, you are going to have n training and validation sets. Okay. All right, and so for just kind of for illustration, I'm going to use this very, very, very simple toy data set. Okay, the toy data set looks like this. We've got the observations 1, 2, 3, 4 in X, and T is going to be 1, 3, 2, 4. And I'm going to let me just skip ahead a couple slides. This is what it looks like. Okay, this is 1, 2, 3, 1, 2, 3, 4 for X, and then T has 1, 3, 2, 4. All right, so we use this toy data set last week when we were just doing kind of matrix operations for ordinary least squares, and this would be the fitted line. Okay, this red line represents the fitted line when you have all 4 data points. Okay, and what we are going to do, okay, when we do leave one out cross-validation, is we leave out one of the observations. In this case, we're going to leave out observation 4. Observation 4 is going to serve as my validation set. Okay, and then the training set will be observations 1, 2, 3. Okay, so we leave one of the observations out. The remaining data is our training data. Okay, so as far as this goes, I've got 4 observations. I'm going to leave out the 4th observation. The other 3 become my training set. Okay, and so when I do, when I write my code, I'm going to write train X is equal, and I'm going to subset X using observations 1, 2, 3. These are going to be, the index I use will be the indices of the training data. So I'm going to subset X using indices 1, 2, 3. And then my T, I'm going to subset T using observations 1, 2, 3. So, and then my validation set will be everything but observations 1, 2, 3. So this is just going to be observation 4. And my validation T is going to be everything but observations 1, 2, 3. So this is also just observation 4. Okay, and then I put those together. I put the training data together into a data frame, and I'm going to call this train data. And I'm going to fit a model to my training data. All right, so I get a linear model. We're going to predict T based on X using the training data. All right, and so this is what the model would look like if I had all 4 observations in my data. Okay, but I'm going to make this dot go away, this one. Okay, observation 4. If that goes away, then I'm left with these 3 data points. Okay, I'm left with these 3 data points. And if I say, give me the best performing, the ordinary least squares line for these 3 data points, this is the line it would predict. Okay, this is the best performing line for these 3 data points. Okay, so this is what I have. And the question here is, okay, if this is my fitted line for my training data, how well does it predict the observation I left out? Okay, and so it looks like if we look at this, it's going to predict the number 3 if I plug in x equals 4. Okay? And indeed, when I compare it to the validation point, okay, the validation point is this green dot, and we can measure the error between what it predicted and what the validation point is, and it's going to say the squared error of this line is 1. Right? So again, here's all 4 data points, and what we do is we're going to say this data point right here is going to serve as my validation set. I'm going to remove it and predict a line on the remaining 3 data sets, or 3 data points. And this blue line represents my fitted model on the training set now, okay? And we're going to measure how well does it predict, okay? How well does it predict an observation it has never seen, okay? So here's kind of our validation point. This was not taken into account when we trained our model. And we say, okay, well, how much error is there? And the error that exists is has a squared error of 1. Okay, and so what we're going to do is we're going to repeat this, leaving 1 observation out each time, okay? And so what we do is we calculate the predicted value, okay, for the points in the validation set. Okay, basically we're looking at where this blue line goes, and we're going to compare that to the actual value. So as far as our code goes, we're going to compare, we're going to create our model based on the training data, and then we use R's predict function. Okay, I guess I'm assuming there's a little bit of familiarity already between with you using LM to create a linear model, and with you using the function predict to make a prediction, right? And so when you make a prediction, you can provide it new data, not for new observations, okay? And new data expects either a list or a data frame. So I'm going to provide it a list of X, okay? And it's going to make a prediction here, and that's going to be my T hat value, okay? And so I'm going to take the difference between the actual T value, okay? This is my valid T, validation set T observation, which, you know, is back here. We subset the original data into a validation X and a validation T, and I make a prediction using my validation X to get my predicted value T hat, and I'm going to compare my validation T value versus the T hat that I predicted. And I'm going to take that difference and I'm going to square it. Okay, and then whatever this squared error is, I'm going to add it to the total squared error, right? And so in the beginning, total squared error starts off as 0, and every time I go through this process, I'm going to tack on the squared error and update my total squared error. okay? And I'm gonna do this 4 times, okay? So far I did it with just this one observation. This is gonna be my first validation point. Then I'm gonna do it with this observation, then I'm gonna do it with this observation, and then I'm gonna do it with this observation, all right? Okay, why don't we pause here, and if this all makes sense as far as the process that I'm gonna go through, give me a little green check mark to let me know that you're following along. And if you've got any questions, throw them in the chat, or give me a red X and we'll try to figure out if there's a way I can clarify. Okay, Gloria, you've got a question, go ahead. And you can ask.
Yeah, so the total squared error always starts out as 0?
Well, you know, as far as I'm doing this is I start off the total squared error with 0, and then I'm going to run basically four iterations of this, and yeah, so it starts off as 0, and I'm going to tack it on. Okay. Later on, I'm going to just kind of store a vector of all of these things, but that's how I'm starting here. Okay. Marco asks, do we do the first quiz question already? No, not yet. Let me give you the first quiz question. First quiz question is E as in elephant. E as in elephant for the first quiz question. All right. So we'll calculate the predicted value here. Okay. All right. So I'm going to go through and do this for all 4 data points here, okay? So we saw it for this data point. Now I'm going to remove this one, okay? So if I remove this data point, I'm going to be left with the other 3, okay? And so what would the best fitting line look like for those 3 data points, okay? It would look like this, okay? So if we remove this observation here, the best fitting line for the other 3 data points will look like this, okay? And we want to measure the error for that data point that we removed, okay? So the data point I removed is this one, and we want to say, okay, we fit this blue line to the other 3, how well does it predict this data point that we left out, okay? And we measure the squared error here, and the squared error is going to be 1.65, okay? All right, I do this again. Here is all 4 data points. This time I'm going to remove this observation here, okay? So if I remove this observation here and I only have these 3 data points remaining, well, what is the line going to look like when we predict it, okay? It's gonna look like this, okay? So when I fit the best fitting line for these 3 data points, the best fitting line is this blue line, and we say, okay, well, how well does this blue line predict the validation point that I left out? So the validation point that I left out is right here, okay? And so how well does it predict this? Okay, we can measure the squared error, and the squared error there is going to be 1.6531. Okay, so this is the observation that I left out, and the squared error is that. Okay, and then lastly, again, each observation gets a turn at being in the validation set. Okay, last one is we are going to remove this data point. Okay, so if I cover up this data point, what is the best fitting line going to look like for the remaining 3? So we have these remaining 3 in a kind of a little triangle here, and we just say, okay, well, what's the best fitting line here? Okay, this is going to be the best fitting line, right? So here's our best fitting line, this blue line, and we say, okay, well, what about this observation that I left off right here? Okay, there was an observation here. How much error is there between the dot that I removed and what this line predicts? Okay, and so I put this back in, and then we say, okay, how much is the error? The error is, squared error is 1. Okay, so if we've been keeping track of all of these, okay, here I have a squared error of 1, I have a squared error of 1.65, squared error of 1.65, and then way back here I have squared error of 1. So if you add all of those squared errors up, the total squared error is going to be 5.306. Okay, so I'm going to have 5.306, and if I take that number and I divide by 4, my mean squared error is going to be 1.326. Okay, 1.3265. So I've taken the total squared error, I've added up these numbers, 1 plus 1.653 plus 1.653 plus 1, okay? That adds up to 5.306, and then the average of those values is 1.3265, right? So I hope that makes sense to everybody, okay? And this was me doing it manually, all right? So I it was a bit of work to make all of those graphs, but I removed the data point and I fit a line to the remaining ones, and then and we calculated the squared error. Okay, I did this 4 different times, and we got this total squared error. If you do it in production, okay, so if you get a job and you're going to do leave one out cross-validation, you will probably not do this manual version of it. Okay, you would probably use this function that that comes with a library boot. Okay, so you'll load up library boot, and there's a function called cv.glm, and this will do cross-validation for you. Okay, and so to use cv.glm, okay, you're going to fit a model, a GLM model, to all the data. So I take all the data. I'm going to create a basically an LM, but we're going to use GLM. And if you don't specify a family in GLM, it's pretty much equivalent to fitting a linear model. But in GLM, you're also able to, specify like family equals binomial, or different kind of families, and fit things like logistic regression and stuff. And if you're in 100C, you'll probably make use of the GLM function. Okay. But anyway, I'm just fitting a linear model, okay, using all the data. And this function cv.glm will perform cross-validation. There's an argument k, and if you leave that off, it's going to perform leave one out cross-validation. And so it's going to go through taking each observation, throwing it out, fitting it on the remaining data, and calculating the squared error. And when you do this, it gives us this value, 1.326531, okay? Which is exactly what we calculated over here. So when we did it manually, we got 1.326531. And when we use R's function, cv.glm, you also get 1.326531, okay? And in your homework, I'm gonna make you do it manually and calculate the cross-validation yourself, okay? And the purpose for that is that I want you to be able to know and understand where this function cv.glm is arriving at this number, okay? Whereas, in practice, okay, if you get a job and you have to do cross-validation, you're almost certainly going to use this function and not some homegrown version of it. But if you only use the functions without understanding where it came from, that would be a problem. So in the homework, you're going to have to do this. Okay. Chazvi asks, what's the difference between LM and GLM? And GLM stands for generalized linear models, whereas LM is just linear model. And so with a generalized linear model, you are able to specify different families of errors. Okay. By default, it's going to be Gaussian, which would be kind of the equivalent of LM. You're expecting your errors to follow a normal distribution, right? Normal distribution of errors is kind of the assumption for a lot of your linear regression models. But you can specify different families, such as binomial, and that would fit like a logistic regression model. And I'm not sure if you covered logistic regression yet in your stats careers, but basically there's a linear component, and the linear component is getting fit into a logistic function, e to the x over 1 plus e to the x type of thing, okay? So anyway, if you don't specify the family in GLM, it's going to act very similar to LM. And the reason why we have to use GLM is because this cross-validation function is expecting a model of the class GLM, and it's going to complain if you give it a linear model. So it's just what you have to do if you want to use cv.glm in R. All right, just a little bit of clarification. When we do cross-validation to evaluate a model, you're going to get a single cross-validation score for that model. It's usually going to be kind of the mean of the cross-validation errors, right? So in our toy data set, when we have 4 data points, we performed leave one out cross-validation, right? And what that required is that we had to fit the model 4 different times, okay? And we produced 4 different cross-validation values, and the total cross-validation is cross-validation score is going to be the mean of those 4 values. Okay, so this is kind of a summary picture, right? So here's kind of the first one. This was the error that we got. This is the error we got. This is the error we got, and the error we got. Squared error of 1, 1.6531, 1.6531, squared error of 1. You add those up, you get 5.306, and you take the mean of these 4 values, and you get 1.3265. Okay, this is the going to be the cross-validation score. Okay, and what we'll do later on in the Olympics data is we are going to fit different models. Each of these different models is going to produce a different cross-validation score. Okay, but each of them we are fitting the same model multiple times to get kind of a squared error value. Okay. So, so you know, after fitting the linear model 4 times or n times, we took the mean squared error of getting 1.3265. Okay, and then what we could do is we could try a different model, maybe like a log-log model or whatever it might be. You're going to fit that other model n times, okay, and you're going to find the validation error each time you fit it. Okay, again, you're going to average all of those things, and you're going to get a different cross-validation score, right? And you would compare the cross-validation score of like the linear model versus the cross-validation score of the log-log model or whatever other type of model it is, and you would compare those. You would not compare like this score of 1 versus this, or the error of 1 versus the error of 1.65. You are not comparing different validation sets within the data. Okay, you're using all of the different validation sets and averaging them to get a single cross-validation score for this particular model, the linear model. You're not comparing them within a model itself. So with that, let me introduce Kfold cross-validation, okay? So Kfold cross-validation is very much like leave one out cross-validation, except rather than leaving just one observation out, you're gonna leave out several observations, okay? And the reason why you might wanna do this is that if you have a big data set, like n different, like 1,000 observations, okay, then you would have to fit the model 1,000 different times, right? Because each time one of your observations serves as the validation set, okay? And so this can become computationally expensive, especially if you're on the order of having like millions of observations, okay? If you have millions of observations, each observation would take a turn at being the validation set. And each time you have a different validation set, you've got to refit the fit the model, and that can become computationally expensive. So so you're going to kind of leave out several observations rather than just one. Okay. The other problem is that because you're leaving out only one observation at a time, the resulting models can end up looking very similar to each other, right? Because the training data for your first run has almost all the data points in common as the next run, the next training set. So so your coefficient estimates end up being very highly correlated, and you still run the risk of kind of overfitting your training data, right? So for large data sets, it's recommended to do Kfold cross-validation. This is going to split up the data into kind of K equal, or at least approximately equal, equal blocks, okay? One block is going to serve as the validation set, and the remaining blocks combine to be the training data, all right? So kind of the diagram is going to look something like this. So here I'm going to take if I do 4-fold cross-validation, I take all of my observed data and I break it up into 4 chunks, right? And each of those chunks, each fold, gets a turn at serving as the validation data, okay? So I would train it on these 3 chunks or these 3 folds. This is going to be the validation set. Okay, I'm going to train it on the other 3 folds, and this will be my validation set. I train it on these other 3 folds. This will be my validation set. Train it on these 3 folds, and this will be my validation set. Okay, so that's going to be Kfold cross-validation. So, so we're going to take a look at Kfold cross-validation for the Olympic data set. The Olympic data set has 28 observations, so I'm going to do 4-fold cross-validation, and that means each validation set will have 7 observations in it. Okay, so here it is. Here's the original data with all 28 observations, okay, from starting in 1896 going up to around 2012. And what we're going to do is we're going to divide the data into 4 random blocks, okay? Each block will have a turn as serving as the validation set, okay? And for each kind of train validation split, we're going to fit a few proposed models. We're going to do a linear model, a quadratic model, a cubic model, 4th order, 5th order, and then 8th order polynomial. And then just for funsies, we're going to do a 17th order polynomial, which is obviously going to be a bad model, but you know, we'll just see how it goes, okay? And in general, as you increase your model complexity, you can get better predictive performance on your observed data that you used for training it. But the question is how well is this going to perform on data that was not used in the training set? How well is it going to perform on quote unquote new data that, how well is it going to generalize to new data that it hasn't seen, okay? And each time we're going to calculate the total squared error for each model, for each validation set. We're going to find the cross-validation score by averaging the squared error for each of these models. And then lastly, we're going to compare the cross-validation scores between the models to kind of select our model. Okay, so to kind of just set this up, all right, I'm going to just arbitrarily set seed 5, and I'm going to shuffle the values 1 through 28. Okay, so I've got 28 observations. I'm going to shuffle those. Okay, and I'm going to basically deal out 7 cards. Yeah, your money's on the 17th order polynomial. Yeah, you're going to deal out 7 cards into 4 different sets. Okay, so we're going to have set A, set B, set C, and set D. Okay, and we are going to deal 7 into each. Okay, so each of these sets has just a random set of 7 observations. Okay, so we shuffle them up using sample. We're going to have random sets of 7. Okay, and then to kind of keep track of all of our cross-validation errors, okay, where to store the results of our total squared error, I'm going to just create some empty vectors. Okay, I'm going to create an empty vector for each of the different models that we're creating, right? So I'm creating a linear model, a quadratic model, 3rd order, 4th order, 5th order, 8th order, and 17th order model, polynomial models. And so I'm just creating empty vectors, each of length 4, to store our errors, okay? And they're length 4 because I'm doing 4-fold cross-validation, which means I'm going to fit the same model 4 times. Each of those times we're going to get a different total squared error, okay? And so this is what kind of our code might look like, okay? So this is just kind of the start of the code. And because I'm doing 4-fold cross-validation, this is me kind of coding it up manually, okay? I'm going to say for I in 1 through 4, okay, the I represents each of these different folds, okay? I'm going to take one of the sets, right? So back here, I dealt out the different indices into 4 different piles, and I put them into a list, and we're going to just take kind of the ith set here, okay? So first, I'm going to take the first set. Set A is going to be my set of validation indices. These are going to be 7 observations, random observations. And I'm going to create my training X and my validation X and my training team validation T. So what I do is I take my Olympic year and I'm going to remove the validation indices. I'm going to do minus V index. I take my the time, the actual time values, and I'm going to remove the validation indices. That's going to form my train X and my train T. So train X and train T will have 21 observations. And then validation X and validation T is going to be the subset of the years for the validation index. Validation T will be the subset of the times just for those validation indices. Okay, so I'm going to combine the training X and the training T into a data frame called train. I'm going to combine the validation X and the validation T into a data frame called valid. Okay. All right. Andy asks, why is the training set without the index in this case, but the opposite for leave one out? Yeah. This is, I just did it this way. Okay. Yeah, for leave one out cross validation, I did it kind of the other way. And in this case, I'm doing it this way. So I think in the leave one out, the indices were indicated by which ones are in the training set. This time the indices are indicating the ones in the validation set. So it was just kind of an arbitrary choice in this. And I apologize for any kind of mix up there, okay? But yeah, so I've got kind of the validation sets here, each one, and I create my training X and my training validation X, and I combine them into data frames. Okay, so I've got a data frame of the training observations called train. I've got a data frame for the validation observations called valid. And N is going to be the length of the validation index. Okay, in this case, N is 7, right? So I've got 7 observations in my validation set, okay? And so to calculate kind of the cross-validation squared error for the linear model, this is how we're going to do it. I'm going to just define model 1 by fitting a linear model where I'm predicting the values T based on X, okay? And here's the key, I'm using the training data to fit the model, okay? So this model 1, the coefficients for model 1 are using only the training data. There's only 21 observations to estimate the slope and the intercept, okay? It doesn't get the full 28 observations that are available in the Olympic. We're only using the 21 observations for to create our slope and intercept estimates, okay? And now I use the predict function using this model that I just created, model 1. I'm using the predict function for model 1, and the values that I'm going to predict for are the new values, okay, in the validation set, okay? So in the validation set, I have valid X, and it's going to use those values to make predictions, okay? And so those predictions we're going to call T hat 1, okay? So these are the predicted values T hat. And then we're going to calculate the total squared error, or the sum of squared errors. And so I'm going to take the observed values in the validation set, validation $T, and I'm going to compare them to the T hats that I just created, T hat 1, okay? I'm going to compare the validation set to the T hats I just created. I take that difference and I square it. I take that difference and I square it. I sum them up and I divide by N. Okay, and this will give me the kind of the first value that goes into the cross-validation for the linear model, right? So I'm storing all of my total squared errors into these different vectors. That will be the first value that goes into cross-validation for the linear model. I do this, I'm going to do this for the second model, okay? So for the second model, I do LM predict T based on the second order polynomial, using, again, only the training data. And then after I've created this model, model 2, I'm going to make predictions T hat using predict on the validation data, okay? I take the difference between the actual values T and the predicted values that I just created, and I'm going to take that difference, square it, sum them up, and divide by N, and I'm going to store it into this vector CV underscore quad. I'm going to do this for all of the different models, okay? And so this is just kind of the start of the loop, and then the full loop looks like this, where I'm doing the same thing for the linear model, quadratic model, polynomial model, order 3, order 4, order 5, order 8, and this should say also order 17, okay? So let me just pause here. And if you're following what I'm doing in this code, give me a green check, okay? And if you are not, give me a red X or something, or ask your questions, and we'll just kind of check in to make sure everyone's kind of doing okay here. Okay, most of you seem to be doing okay. Some of you haven't responded, but nobody's given me a red X so far. So, so I guess that's okay then. Okay, so just visually, this is what it looks like, okay? So here is all 28 observations, okay? And I've indicated, so we're gonna just investigate one of the 4 validation sets, right? So I have a total of, you know, set A, set B, set C, and set D. And I think set C just happened to be interesting, so, so I'm going to use that, okay? And so here's the original data, okay, all 28. And these red dots, the 7 red dots here are my validation set, okay? So these are the validation set. And so what's going to happen is I'm going to remove these red dots. I have 21 dots remaining, and I'm going to fit my models on the 21 remaining dots. I'm going to fit the linear model on these 21 dots. I'm going to fit the quadratic model on these 21 dots. I'm going to fit the cubic model on these 21 dots, okay? And then for each of those fit models, we're going to see how much error there is between the fitted value versus these 7 dots in the validation set. Okay, so if I remove these 7 dots, for these 21, this is the best fitting linear model for the remaining 21 dots. Okay, so these are this is the best fitting model for the remaining 21 dots. And then I say, okay, well, how well did this linear model predict the red dots that we left out? So we put the red dots back in and we say, okay, well, how much error is there? And so for some of the dots, the linear model predicted very well. But for a few of the dots in the validation set, it did not do a great job. Okay, so there is some error here and some error there. And so if I take the mean squared error here, I'm going to get 0.0319. Okay. Here is the training set, the 21 dots, okay, and I fit a quadratic model on the 21 dots, okay. I'm going to, so again, I removed the 7 dots. This is the training model fit on the training data, this 21 dots, and we say, well, how much error is there for the 7 dots that we left out, okay? So these are the 7 dots for the linear model, the same 7 dots, but now for the quadratic model, and we can see the mean squared error is a little bit different, okay? We do the same thing for the cubic model, okay? Cubic model, we fit it to the 21 dots. This is the best fitting cubic line that exists for the 21 dots, okay? And we say, okay, well, how much error is there for the 7 dots that we left out in the validation set, okay? And we do this and we get a mean squared error, right? Does this kind of make sense what I'm doing here? Here it is for the 4th order polynomial, okay? So we fit the 4th order polynomial on the 21 dots, okay, 21 dots. And then we ask how much error is there for the 7 dots we left out, okay? So here are the 7 dots we left out, and this is the curve that fits for the 4th order polynomial, and we can calculate it, right? And so when you look at the 4th order polynomial, it starts to curve up here, and that actually produces, you know, a fair amount of error for the validation set, okay? Here it is for an 8th order. So when we fit an 8th order polynomial, it gets more and more squiggly, okay? And it's trying to fit the 21 dots that we observed. It's trying to minimize the errors in the 21 dots, okay? Because this is the training data. And we can see, you know, in the 8th order polynomial, it starts to curve back up, saying that as after the 2008 Olympic Games, the 100-meter dash is going to get take even more time, which, you know, doesn't really make sense. And so when you calculate the validation error, this prediction doesn't do a good job, okay? It's you get more error here, okay? All right, and let me just show you what the 17th order polynomial looks like, okay? with the 17th order polynomial, this is the fit, which is, you know, totally crazy, okay? But what it's doing is it's trying to minimize the errors in the training data. And it does a really good job for these observations, right? There's no error on basically these observations. You know, it's fitting a really squiggly line to try to minimize the errors on the training data. But where we don't have observations, like right here and right here, because these observations exist in the validation set, like right here, we can ask, does this generalize well? Or is it able to predict the missing observations, okay? And when I throw them back in, we can see it does a terrible job, right? It's because it was trying to minimize the errors on the training data, it's going to create really bad predictions for these observations it hasn't seen, okay? And so this observation, which is over here, it's predicting like way off here, off the chart, and so our total mean squared error is this ridiculous 1,600, okay? Whereas everything else was kind of on the order of around, you know, 0.03 or something like that, okay? So this is doing a really bad job, okay? And so if we keep track of these, you know, I did this for all of the different validation sets, okay? And so for validation set C, you know, we could see we got this. And basically what we're doing is we would run that operation for all 4 of the different validation sets, and we would take the average, okay? So the average cross-validation score, the mean, is 0.0674, 0.0624, 0.0571, 0.0661, 0.0644, 0.0419, 525, 0.367, okay? And you would look at these average cross-validation scores, and in general, you would pick the lowest cross-validation score, okay? Now, coincidentally, okay, so we look at this, and the lowest cross-validation score is actually the 8th order, followed by the 3rd order, okay? So we have 0.0419 is the lowest and 0.0571, okay? And so we go, okay, well, does it make sense to pick the 8th order polynomial, all right? And so here's one of the things is that when you have Kfold cross-validation, there's randomness as far as which observations end up in a validation set. And so it's possible that just by coincidence, a poor model just happens to have the lowest cross-validation score, right? And so you say, well, does it make sense to use an 8th order polynomial to make predictions? And I would say probably not, okay? And so it's often recommended that you would run cross-validation more than once, okay? Just so that you don't accidentally pick. If you're just blindly picking the one with the lowest cross-validation score, you would say, oh yeah, let's use the 8th order polynomial, okay? Probably not the best idea to just blindly go with absolutely the lowest cross-validation score. So here I just run it again, okay? With a different seed, okay? And when I run a different seed, 3rd order polynomial ends up being the lowest, okay? And the 8th order polynomial doesn't perform as well. It actually ends up being the 2nd worst, okay? And then when I come over to here and I do another random seed, 3rd order polynomial is the best, and the 8th order polynomial ends up being performs better. But overall, what we can see is that in the 3rd order polynomial is consistently the best or the 2nd best, whereas the 8th order polynomial, its performance is all over the place. It's either going to be you know, best, 2nd best, or the 2nd worst, okay? In all of these cases, the 17th order polynomial performed really terribly, okay? And then the other ones, like the linear model, is consistently not a great performer, okay? 0.0674, that's the 2nd worst here. 0.0632 is the middle of the pack. 0.0708 is, again, middle of the pack. So, but the 3rd order polynomial seems to consistently be the best, or the 2nd best. So depending on the seed, it's possible to get a cross-validation result where a suboptimal model happens to perform best, okay? If you're able to afford the computational expense, it's recommended to run cross-validation more than once. Okay. The 2nd quiz question, that's a reminder there. Okay, 2nd quiz question, answer is C as in cat. C as in cat is the answer to the second quiz question, okay? All right, so let me just kind of, I know I'm a tiny bit over time, but basically you can do the same thing, cross-validation with using this GLM function, cv.glm, and you would run this kind of a few times. When I run it a few times, we're gonna get slightly different values, okay, when you do Kfold cross-validation. And again, it's because there's some randomness as far as which values get put into the validation set, all right? And the same goes for all of these other things, okay? When you do leave one out cross-validation set, there's no variation as far as what the validation set is, okay? Each observation serves as a validation set exactly one time. So if you run cross-validation GLM for leave one out cross-validation, you're gonna get the same value every single time, okay? All right, so to summarize, cross-validation is a way for us to see how well a particular model is able to predict values that were not used in the training portion. So you train on a certain set and you say, okay, well, how well are you now able to predict values that you haven't seen? And that's what cross-validation does, is it measures that performance in predicting new values. And the goal is obviously to have the lowest amount of errors in terms of predicting the new values that it hasn't seen. So this is an important strategy that is used quite frequently in machine learning for model evaluation. And so you will do this and encode this up in your homework, and we'll go, good luck with that. Okay, I'm going to stop the recording here.